Mark Labrie. I'm with the aerating mixer station, and we're going to present today the steady state analysis and step response analysis for our system. Our team consists of myself, Matt Baltimore, Michael Newman, and Michael Sherritt, and we're from the University of Tennessee at Chattanooga. Today I'm going to give you a brief system overview, and then I'm going to talk about the steady state operating curve for our system and the step response analysis that we did thereafter. And then I'm going to have a conclusion. Our system basically works like this. We have a manipulated variable, which is the input percentage to the motor. It goes through the mixer drive system, and then it comes out as the control variable as the output speed or RPM. This is the basic layout of our system. The speed recording controller would be here, and it would send a signal to the controller that starts the motor. The motor then starts the shaft power that goes through the gearbox and begins the speed of the system. The amount of input percentage that we put into the motor will yield the amount of speed that we get out of the gearbox obviously to roll the mixing station. And that would be the output variable that we calculated and ran our data on. So here's a sample of the data from the experiment. This is the speed versus time plot for the steady state of this system. As we can see here, it took about 0.6 seconds for the system to become steady state. It evened out at about 75 RPM with a deviation of about 6 RPM. Therefore, the 75 plus or minus 12 RPM for the entire system. The transients was very short-lived in our system, and actually, the more input percentage we put in, the less actual variance we got. I do not have a picture of 75%, but it was more of a realm of 3 RPM percent of deviation. From these, we calculated the steady state operating curve. For all of the averages, we therefore got points for every 5% interval that we did for our system. As we can see on the steady state operating curve, it is extremely linear. The operating range for our system is from 0 to 100% and from 0 to 1750 RPM. It's absolutely linear. We can completely tell, well, not completely, but with some sort of tell what we're going to get out of the output from the input. We did the operating ranges from 0 to 25%, from 25 to 50%, 50% to 75%, and 75 to 100% split between the team members, and therefore it's shown. Here is the step response analysis. This is going up the step from 5 to 25%. We did not do the 0% step for it gave us 0% output. This is from 5 to 25%. We came from 5% to 25% on the blue line, which would be your input value for percentage, and the output control value is the red line. Now we can see from this that the dead time of our system. Actually, that's the next slide. The gain of our system was 17.4 RPM per percentage. Now, if we were to look at the steady state operating curve for our system, we actually concluded that the slope of this line was also 17.4 RPM per percentage, which would agree with what we discussed in class. So there was a jump of 20%, like we discussed before, and of 350 RPM for this particular curve. We redid the curve again for going down. From this is the same curve, but this will show you the dead time, which is TO, and the tau, or the time constant of the system. Now we can see from here that our dead time is slim to none. We have a dead time of about 0.1 seconds, and we have a time constant of about 0.4 seconds. The system went extremely quickly. We did from 0 to 10 seconds to get steady state, and I shortened it to 2 to 4.5 seconds to be easily seen. Now, this would be the step down for the same function. This is pretty much exactly the same. All of our experiments turned out very, very, very similar. Of course, with the only difference being the averages of the steps. Now, this again is a 20% jump with 350% between the steady states. And again, we got the exact same gain of 17.4 RPM per percent. Now, if we look forward, this is again the variation for the dead time and the time constant of our graphs. again, we got very similar values of 0.1 seconds and 0.4 for tau, the time constant of these graphs. These are all of the gains for all of the systems that we did. We ran 3 up and 3 down for the 4 operating ranges that I described before from the 25% increments. As we can see, there's very little differentiation between all the systems. The 17.4% RPM per percent for the gain seems to hold true for most of the system. We had some deviation for the up step between 75 and 100%. We're very unsure why. That's what we calculated with the data. Then with our dead time, it actually seemed to rise. The dead time seems to be the only thing that changes between systems as we increase the input percentage. With the input percentage raising from 5 to 25 by only about 0.01 seconds, up to the, say, 5 to 100% at 0.05 seconds. So our dead time is fairly short by comparison to our 2-second experiments. And then our time constants seem to vary awkwardly for all of the experiments. But we have an average of about 0.35, as we can see, plus or minus 0.5%. And again, the time constant is very short, 0.4 seconds. We didn't have to run experiments incredibly long to get to steady state. And in conclusion, the steady state operating curve shows extreme linearity between the input percentage and the speed and RPM. The operating range of the system is 0 to 100%. Again, it's also 0 to 1750 very linearly for the RPM. All the ranges, including the upper, the lower, and both the mid ranges, all operate alike. The three steps that we actually did for each step response for up and down, the graphs look exactly the same. And so we had very little in terms of uncertainty for any of the graphs. We basically got the same results for all of them. The system increases the output as the input increases, and the gain of the system is calculated to equal the slope of the steady state operating curve, which is expected. Also, the dead time grows as the input increases, which is what we found to be true for our system. And time constant seems to be around 0.35 plus or minus 0.05 seconds. And the system time constant responds similarly for all the experiments. Again, up to 0.25 seconds. And that would be their mixer station. Very, very straightforward system. We have very little deviation. Is there any questions? Thank you for your time.